Today I'm going to talk about the problem with the boundary at African plate. The African plate is surrounded by ridges, and there are no subduction zones around it. Therefore, on the diagram, I use spread arrows to indicate the direction of the spreading of ridges around the African plate. The spreading rates on either side of the ridge are different, causing the African plate to grow in the east, west, and south direction. The problem is the ridge around the African plate do not correspond the downwelling limbs of a convection cell. Why does mantle melt and upwell at the ocean ridge? The two plates separate from each other at ridges, creating a vertical gap beneath the mantle with each equation. This necessitates the essence of the mantle to fill the gap. The mantle is composed of crystal with various melting points, and at each ascent, the decrease in pressure led to a reduction in the melting points by 5 to 10 degrees per kilopascal. Consequently, crystals with lower melting points in the mantle begin to melt, resulting in partial melting，然后就形成了新的板块、新的地壳。Why does plate subduction take place? Older plates subdue into the metal at subduction zones. During the subductional process, rocks undergo metamorphism, transforming from hydroxide basalt to a high-density rock known as eclogite. The gravitational force acting on the plates prevent facilitating plate expansion at the ridge. Does plate geometry correspond to metal convection cells? I think plate geometry does not fit well in metal convection cells. For example, the subduction of the 质力 rise beneath upwelling and downwelling convection limbs cannot be in the same place, so spreading center cannot correspond with the outwelling limbs of major convection cells. Moreover, the African and 南极大陆板块 are mostly surrounded by ridges but with no associated subduction zone that could be a downwelling limb of a convection cell.
Here, there is a mistake in the arrows. Do you know which one?
欧亚大陆这一块对不对？
对，那里应该是什么？
应该是隐没区域。
北边其实是隐没带，
隐没带。
东边、西边、南边都是张裂带。
对。
Very good, thank you.
Does the mantle convex and which geological feature corresponds to the upwelling limb of mantle convection cell? Does the mantle convex? My answer is yes, because the Earth undergoes convection. The mantle is a layer of rock that lies beneath the Earth's crust and extends to the depth of about 2,900 kilometers. It is composed of solid rock that can flow over geological timescales. And the convection is driven by heat for the Earth's interior. Radioactive decay of isotopes and residual heat from the planet's formation contribute to the heat in the Earth. This heat causes the rock in the mantle to become semi-fluid and undergo convection currents. And the process is similar to boiling water in a pot. In the mantle, hot material rises from the deeper region, and cooler material sinks, creating a continuous circulation. And the movement of tectonic plates at Earth's surface is influenced by these convection currents in the mantle. And the second question is, which geological feature corresponds to the upwelling limb of mantle convection cell? The upwelling limb of mantle convection cell corresponds to a region where hot material from deeper Earth is rising toward the surface. I have two volcanic features. One is mid-ocean ridges. It is the underwater mountain range where new oceanic crust is formed as plates diverge. And the upwelling of mantle material is responsible for the formation of this volcanic feature along the mid-ocean ridge. And the second one is hotspots. Hotspots are locations where the plumb of material rises from deep within the mantle to create volcanic activity at the Earth's surface. As the plates move over the hotspot, the chain of volcanic islands of seamounts may be formed, and the hotspot represent the upwelling limbs of the mantle convection cell. In summary, the upwelling limbs of mantle convection cell is associated with the creation of volcanic creatures, including mid-ocean ridge and hotspot, where molten material rises from the Earth's mantle to the surface.
Can you explain this figure? As far as I know, I think this represents the Rayleigh number. The lower figure compared to the upper one has higher Rayleigh number. What the figure trying to tell us, I think, is the higher Rayleigh number is the more its convection will be, and it's getting more chaotic. You can see the lower one is more messy compared to the upper one.
Very good.
可以请解释一下两种地壳均衡学说，还有它们适用的场合。
One is no flow and no compensation, and one have flow and compensation. 就是那个地含那些流。
We want to talk about plate tectonics. What textbook said is not plate tectonics. The authors said they want to talk about mantle convection and its relationship to the surface. So you need to know that plate tectonics is closely related to the mantle. When we talk about plate tectonics, I will ask you about your perception of plate tectonics. Usually, Taiwanese students, if they are not doing something else during their high school earth science course, they will be able to tell you something about the plate tectonics of Taiwan. They can talk about maybe the mid-ocean ridge or the 环太平洋火环. I would say that would be your major perception of plate boundaries. For the Earth, there are many plate boundaries. If I'm a scientist who need to study plate tectonics, I actually need to study, okay, what is this one? How about this one and this one? So what is the Pacific plate? How about their boundary type? There are basically three types: divergent, convergent, and translational. So how about here?
也是聚合型，
Right, convergent. How about here?
那边是张力的，
Divergent. How about here?
也是聚合。
Very good. For the Pacific plate, we have convergent boundary at the west and divergent boundary at the east. And this boundary here is the oceanic ridge of the Pacific Ocean. When you think about mid-ocean ridge, you always think of this one, because this one is so typical, exactly at the middle of the ocean. But actually, every ocean has its ridge. It's just a different part. For the Pacific, it is at the east. That's the reason why in Taiwan, very few scientists study hydrothermal system, because the ocean ridge is the place where you can study hydrothermal system. For the Indian Ocean, it's very strange. This and this, they are both its ocean ridge. This is a very strange spot called triple junction. Pacific plate is sort of classical in another way, because if you think about mantle convection, here you probably have upwelling. The ocean ridge produce new crust. And here you have subduction zone, subduct old plate. So it is like conveyor belt. Let's talk about African plate. This is the ocean ridge of the Atlantic Ocean. This is the ocean ridge of the Indian Ocean. The African plate was actually bordered by divergent plate boundary at the west, at the south, and at the east. The only subduction zone is here. So what would be the problem? If you consider the classical mantle convection cell concept, I have production of new crust here and here. The African plate should bulge up, because there's always new crust being produced. At some point, there's no space to accommodate new crust. And what is your perception of the mechanism? Please correct me if I'm wrong. In your high school, are you still teaching this kind of graph? All right? This graph is so well rooted in everybody's mind. Whenever people talk about mantle convection, they always come up with this graph. But today we want to say this graph is not very accurate. That's the message we want to deliver in today's lecture. Apparently, there is some problem. In this graph, it says the mantle upwelling limb is oceanic ridge, the downwelling limb is subduction zone. But here I just said, in the case of the African plate, I have divergence zone here, divergence zone here. Where can I accommodate my crust? We will come back to our question later. We need to first talk about the issue whether there is mantle flow or not. The more a mountain is eroded, the higher it is. Why is that? Why shouldn't it be shorter? Why is it higher? This is because of isostasy. Floating plates on the asthenosphere must displace a mass of liquid equal to their weight, following the Archimedes principle. Eureka! There are several scenarios proposed to explain the Earth's topography. This is closely related to whether you think the mantle has flow and whether you think there is isostasy or not. The first one is the easiest one. Everything is rigid. This is our mountain. We have mountain and valley. We have different elevation here. These different elevation, they may have different density, but it doesn't matter because below them, there is another block or mantle, which is also rigid. So these are rigid blocks sitting on another rigid block. When you see different elevation, it simply means the blocks have different height. The second scenario is the mantle has flow. In this scenario, every block has the same density of 2.65. This is the density we use for continental crust and also for marine sediment. Therefore, when you see a high mountain here, beneath the high mountain, it has an even deeper root. It's like iceberg. Based on the Archimedes principle, the higher the mountain here, the deeper the root it will have. Here, there is a depth of compensation, which is the deepest depth that the root penetrates. It has to push away the fluid in order for it to sit in the fluid. The third scenario is when you see different elevation, it is a combination of different density but same thickness. Then we see different elevation. The tallest one will have the lowest density, and the deepest one will have the highest density. Which one better explains the Earth's topography? I guess you know what I'm going to tell you. Of course, this one. But this one, in a way, also makes sense. Of course, we know for the Earth, we don't have same thickness. But for the Earth, we know we have oceanic crust, which has this density, and we have continental crust, which has this density. So the combination of this one and this one will be closest to the Earth's topography. So now I want to introduce a geophysical concept, gravity anomalies. Here, we have different scenarios. The first scenario is like this one. Everything is rigid. We have a low density block sitting on another high density block. The second is like this one. The bottom one is fluidic. So the upper block has a root. You are sitting here and here at the same elevation. According to Newton's third law, the gravity you measure at radius r is equal to the gravitational constant, which is a constant, and the m, total mass enclosed within radius r. The radius r is the depth here, and this is also r. In these two scenarios, they have the same r, and then the small g here will be related to m, the mass below the point here and here. My question for you is, when measured at the same elevation, which observer will detect higher gravities? Remember, both cases, they have the same r. The only variable is big M, total mass enclosed within radius r.
Also the right-handed one.
Exactly, the right one. Because the right one, all the way down, it has a density of 3.3. But for the left one, for a certain depth, it has only a density of 2.6. Therefore, if you integrate the mass, the column here will give you higher mass. Therefore, we usually detect negative gravity anomalies. When we say negative anomaly, it means because this block has a root, you will detect lower gravity than this one. Then we say it's negative gravity anomaly. This is an anomaly map of Taiwan, and you see that here and here we have negative anomaly. And because we have negative anomaly, scientists confirm that mountains have roots. And because mountains have roots, scientists further conclude that mantle is ductile. For our 3 research vessels, New Ocean Researcher 1, 2, 3, we have gravity instruments set up at NOR1. It is used to generate this kind of map or data. That's the first evidence, some gravity measurement. The second is the so-called post-glacial rebound. During the glacial period, glacier will build up, and ice cap has a lot of weight. And because of its weight, it will add pressure to the mantle. And then mantle is pushed away. During interglacial period, the ice melt away, so the weight is lifted. Because of that, the mantle can gradually come back. At the end, it will level off. This process is very, very slow. The last glacial period is 15,000 years ago. At that time, the center of the ice cap is around this area. However, last 8,000 years, the Hudson Bay, which is this area, it is still uplifting. Mantle, even we know it's ductile, it is not as fluidic as seawater. Does mantle convect? Based on the geophysical data, the gravity data, and geomorphological evidence, the post-glacial rebound, scientists confirm that mantle is indeed ductile and may flow. But what is the mode of the movement? Rayleigh number is used in fluid dynamics and is dependent on several parameters. The most important part, the first one is delta T, the temperature difference along a distance. In our case, you need to know the temperature difference between the core mantle boundary and the crust mantle boundary and the distance here. This is the thickness of mantle. The higher the temperature difference and the larger the distance, the higher the RA value will be. However, RA is inversely proportional to viscosity. The more viscous the material is, the lower the RA value is. How about the viscosity of mantle? It is 10 to the 24th times greater than water. It's almost solid, right? In fluid dynamics, there's a threshold value. When the Rayleigh number is higher than 2000, convection is inevitable. You can use this parameter to determine whether the material can flow. Scientists, after some calculation, they figure out that the Rayleigh number of mantle is 10 to the 6th or more. And this graph corresponds to a Rayleigh number of 10 to the 5th, and this graph corresponds to a value of 10 to the 7th. The difference between the upper and the lower one is the upper one is regular convection cell, upwelling, downwelling, upwelling, downwelling. But the bottom one is 2 orders of magnitude higher, so you start to see this kind of feature. In fluid dynamics, this is called turbulence. So the mode of movement of mantle is between this and this. So far, we have talked about 3 lines of evidence. We talk about isostasy, post-glacial rebound, and the Rayleigh number. Geophysical and geomorphological evidence confirms that mantle is ductile and may flow. And modeling work suggests that mantle convects. We confirm that mantle is not rigid, it's ductile. But the next question is, can mantle flow explain plate tectonics? We want to see if there is a connection between this and that. That will be the next section, mantle flow and plate tectonics. That was in our assignment. We discussed whether there is a simple relationship between plate boundary and the mantle convection cell. Because in this graph, it's a very typical graph, it says the upwelling limb of the convection cell corresponds to ridge, and the downwelling limb corresponds to trench or the subduction zone. This is so classical. It's deeply rooted in everybody's mind. But actually, there is no such simple relationship. Final nail in the coffin, subduction of a spreading center. This is a very famous place in plate tectonic study. Vancouver is here. Here it is a subduction zone. This is a North American plate. This is Juan de Fuca plate. It is a smaller plate next to the larger Pacific plate. This is ocean ridge. The ocean ridge is actually being subducted. If you recall this model, this and this should be fixed at one spot. The ridge should always be ridge, subduction zone should be always subduction zone, and ridge will not be subducted. However, in reality, it's not the case. Spreading center can also be subducted. This argues against the convection cell representing plate boundaries. There is another piece of evidence. In the 20th century, humans start to send a lot of GPS satellites into the space. It is now a very popular method to monitor the motion of the Earth. In Academia Sinica, there is a group who set up a lot of GPS stations in Taiwan to monitor the motion of the ground. For the globe, there are also a lot of GPS stations. Using that, scientists can monitor how the plates really move. And scientists realize that the ridge is also moving. It's also gliding. Measurement from the GPS show that the plate is moving and the ridge is also moving. It looks like the ridge is not really fixed at one place. This explains why in the African plate we have spreading center here and we have spreading center here, but why doesn't the African plate bulge up? Because this can move and this can also move. That's the major revision for you today regarding the classical model of plate boundary you learned from your high school. For the spreading center, it is not active upwelling. In terms of active upwelling, your perception is mantle upwells first and push away the plate. It results in the ocean ridge. That is what you learned, or what I learned from my high school education. This is so-called active upwelling, but this is wrong. It is not the deep active mantle convection that results in spreading. The real situation is passive upwelling. It is the spreading of crust that induces mantle upwelling from shallow depths. The plate here is pulled apart first. And because the mantle is ductile, if there is a gap here, liquid will come in to fill the gap. That's the reason why mantle will ascend. You learn from our previous topic, rock usually melt when they ascend. So this is what we called pressure release melting. Because of reduction of pressure, therefore the reduction of solidus, that leads to the melt of rock. The melting depth will not be too deep, as shallow as 100 kilometers. The thickness of mantle is 2,000 kilometers. So 100 kilometers is really shallow. So this has nothing to do with the upwelling limb of the mantle convection cell. How about subduction zone? Subduction cannot be a shallow process. This is confirmed by seismic study. Every time an earthquake happens, the observatory around the globe will try to position the epicenter. They will not just provide the coordinates, they will always provide the depths. You can collect all the data, you can map the epicenter. This transect corresponds to the map here. This is Japan. Off Japan, there is a change here. This is A, this is B. Each dot here is an earthquake. You can see that the earthquake do not randomly distribute. They actually distribute along a specific zone. This zone has a specific name called Benioff zone. Based on the Benioff zone, the data of epicenter, scientists found that the distribution of earthquakes in subduction zone is down to 700 kilometers. It's much deeper than the spreading center, where we know the source of magma should be shallower than 100 kilometers. So far is the classical data. Starting from 10 or 20 years ago, there is a fancier method called seismic tomography. This term might be new to you. However, I think over the past 3 years when we have COVID, you must have heard of the term CT. CT means computer tomography. Seismic tomography has the same principle. By processing the seismic wave in a different way, you can probe the interior of the Earth. Look at the bottom one first because you are more familiar with Japan. This is Japan. This is from west to east. So this corresponds to this data here. But this is epicenter and its data is only down to 700 kilometers. And this is seismic tomography. This is down to CMB, core mantle boundary, down to 2,000 kilometers. And what are the colors here? They are seismic wave velocity. Seismic wave, its velocity is dependent on 2 parameters. The first is the phase of the matter, whether it is solid or liquid. The second is the density of the matter. High density will provide higher velocity, and low density will provide lower velocity. The blue-colored patches is the high velocity part. Generally, if the material is under higher pressure and is colder, it will give higher seismic wave velocity. The red part has the lowest velocity, so it's something hotter with the lower pressure, lower density. Starting from the change down to the core mantle boundary, there is slab-like material which has high density. This will give you the impression that this is the subducted plate. And you can see patches here. It looks like subducted plate resting on the core mantle boundary. This is another case. This is Central America. This is West and East. In Central America, we know there are also earthquakes like Haiti. There they have a subduction zone and they can also find the same feature. Based on seismic tomography, scientists concluded that yes, subduction zone is indeed a very deeply rooted feature correspond to the downwelling limb of the mantle convection cell. What causes plate to move? It is now generally accepted that plates glide over mantle rather than riding along with mantle convection cell. If you recall the history of plate tectonic theories, it's a little bit like continental drift was proof. Up where magma comes from shallow depths, less than 100 kilometers, where a subducted slab may descend down to the core mantle boundaries. So, what causes plate to move? The mechanism generally accepted by geoscientists is slab pooling. And the reason why this happens is the density difference of rock. Last week, we already announced that the density difference between continental crust and mantle is huge. Here we are talking about oceanic crust to eclogite. From the ocean ridge where it is fresh to the subduction zone where it is already old, the basalt will get hydrated, so its density will be 3.0. Once it enters the subduction zone, it will be squeezed, then it will undergo metamorphism. It will turn into amphibolite and later to eclogite. Its density is increased over time from 3.0 to 3.6. Mineral will undergo phase change to high-density minerals. The denser mineral will act as a dragging force. So the ultimate dragging force of slab pulling is these high density mineral. Last time I asked you, do you think the density difference from this one to this one is it large? In your daily experience, you will say, no, it's not large. However, if you compare the density difference of this to thermal hotline circulation, the density difference from this one to this one is about 20%. And for thermal hotline circulation, the density difference is probably less than 10% or even 5%. This small density difference in seawater is enough to trigger thermal hotline circulation to make sure our deep ocean will not be anoxic. And here we have 20% of density difference. It's actually huge and triggered the plate tectonics. In the textbook, you will also see ridge push. If you check the submarine topography, you will see that in the ocean basin, the ocean ridge usually has the highest elevation. Therefore, ridge push means the ocean ridge actually has higher potential energy, so it sort of push the plate in this direction. Here, we have dragging force, and at the other side of the plate, we have pushing force. Push plus dragging triggers the plate subduction. But the dragging force here play a major role in triggering plate tectonics. Here we have subduction, and this is a deep feature. And in another side of the plate, we have ocean ridge, where we have mantle upwelling, but it's a very shallow feature. If we think about this graph, the downwelling and the upwelling should both have very deeply rooted base. So if this or this do not correspond to ocean ridge, where can we find this? Because the mantle must upwell, otherwise the mass will not be balanced. So this must happen somewhere. And where is it? This. That's another major correction for the plate tectonics model you learned from your high school. The upwelling limb of mantle convection cells is not the ocean ridge, but the mantle plumes. If you go to museum very often, you will always see poster for mantle plume. For you, mantle plume is probably an individual concept that has nothing to do with plate tectonics, I guess. But actually, mantle plume play a major role in plate tectonics. It is intraplate volcanism. People also call it hotspot. While 90% of Earth's current volcanism is associated with plate boundaries, a significant number of volcanoes occur in the middle of plates. There are very famous examples like Hawaii, Yellowstone, etc. The magma of hotspots has a deep origin. There are several evidence to support this. Geochemical, geophysical, and geomorphological, but we will not talk about all of them. We will only show you the first two evidence. We first talk about geochemical evidence. That's the time we will introduce the method scientists use to date volcanic rock. That is potassium-argon dating. Potassium-40 is the most abundant radioactive nucleus in seawater. It's very abundant in rock, so it's also very abundant in seawater. It will decay to argon, which is a gas. Its half-life is 1.3 times 10 to the 9 years, so it has a very long half-life. Okay, how it works. In Taiwan, it's possible to do this, but it requires very special instrument. In molten rock, which means when the rock is melted, argon-40 will escape to the atmosphere. So if it was ever produced by potassium-40 and it is locked in the crystal, when the rock is melted, argon-40 as a gas can escape to the atmosphere. When the magma is cooling down, and when the rock starts to recrystallize, argon-40 will be trapped in the lattice of minerals or in the crystal. You might think in mineral everything is solid, but actually in mineral crystal it's possible to trap gases. When potassium in the mineral structure start to decay to argon-40, The argon-40 can be trapped in mineral crystal as long as the mineral is solid. Therefore, the potassium argon H represents the most recent volcanic activity. If this piece of rock, after it crystallizes, is melted again, then it's an open system again. The clock is reset. The potassium argon H you measured is the second volcanic activity, not the first one. Argon-40 can be measured by dissolving the rock under vacuum for spectrometric analysis. You have to put the rock into a container and you need to evacuate the gas because you know argon is relatively abundant in the air. Afterwards, when you make sure the vacuum is good enough, you dissolve the rock using hydrogen fluoride. And then the argon trapped in the crystal will be released. Then you collect the argon and send it for measurement. That's how people do this kind of dating. Age of volcanic rocks. This is the Pacific Ocean. There are many, many island chains, and they seem to be parallel to each other. One here, second here, third here. Scientists go to these mountain chains, collect rock from these, and measure their potassium argon H. This is the distance from Hawaii. They realize that the more distant the sample is from the Hawaii, the older age the rock will have. How to interpret the graph?
Because there's a hot spot in Hawaii, and the hot spot won't move, but the crust will move. When the crust moves, the age become older.
How can you exclude the possibility that the magma source is actually moving in this direction? The magma source was initially here, and somehow it is migrating, and now it is at Hawaii. That is also possible, right?
我只是想问，那两个也是热点吗？
是。
那有没有可能他们三个的路线很像，所以他才会猜是不是热源不会动，是板块在动？
Yeah, these volcanic rock, they are almost parallel. They have nothing to do with oceanic ridge. The oceanic ridge or Pacific Ocean is at the very eastern part. If they are three independent hotspots moving beneath the Pacific plate, it doesn't make sense that they should move in parallel. So the most reasonable explanation is the hotspots, they are fixed at the same position. And what is moving is the plate. That will best explain the feature here and the feature here. And the second question is, what is the slope? Slope is the result of linear regression, but it will give you a physical meaning. What is the physical meaning of the slope? I mentioned many times in geochemistry, we like to use slope.
它是板块移动的速率。
Very good. The slope is the subduction rate or the moving velocity of the Pacific plate. You see, it's distance divided by time. 我在问你斜率的时候，你就需要就是看单位，看单位你就可以很快猜到它的物理意义是什么。有时候你是要拿 y 除以 x， 有时候你要拿 x 除以 y。我都可以举好几个例子，什么大霹雳的时候也是叫你看斜率，等时线也是叫你看斜率，10210沉积速率也是叫你看斜率，在这边我们也是叫你看斜率。Again, we want to use the fancy seismic tomography to scan the underground world. This is from seabed to lower mantle. And these are the names of the small islands. The color patches here are seismic wave velocity. The warmer color means low velocity part. Beneath these individual small islands, there is a huge magma chamber. So we have these low velocity fingers beneath the small islands. Therefore, seismic tomography shows us that yes, beneath these small islands produced by hotspots, we have a lot of magma. So they are indeed deeply rooted structure. I think hotspot is still relatively new to you. So where can we find hotspots? They are more widespread than you think. Here are the known locations of hotspots. I think it's not complete because in the Philippine Sea Plate, which is our neighbor plate here, it also has hotspot. So these are just a few major hotspots that we know. The upwell magma in mantle plume balance the mass introduced by subductive slab. So here I can point out a few spots on the map where we have hotspots that produce major submarine topographic feature. If you look at the world's map here, there are many places with very strange feature. Like this one. This is produced by a hotspot along the way when this continent collides with the Eurasia plate. During the whole process, there's a hotspot working here. It has recorded all the way. And here, this one is also hotspot. This one is also hotspot. They are actually more abundant than you know. These are the well-known major hotspots in the oceanic crust, but they are smaller ones. But the smaller ones are not that easy to detect, so it requires more investigation. I will conclude with this final figure. After several decades of investigation, what we know about plate tectonics and its relationship to mantle convection. First of all, we know that mantle convex, and the mantle convection is probably not regular convection cell. For the ocean ridge, is a small rupture of the Earth's skin, ultimately created by subduction zone. The subduction zone, based on seismic tomography, is a very deep feature. You can trace the subductive plates all the way to the core mantle boundary. Because subduction will introduce more silicates back to the mantle to balance the mass, there must be upwelling, and the upwelling should also be deeply rooted. Scientists believe that the upwelling part is mantle plume, because seismic tomography show you that mantle plume is a very deeply rooted feature. And the most interesting part from the seismic tomography is beneath the African plates and Pacific plates, they found two major low shear velocity provinces, here and here. This is believed to be the graveyard of subductive plates. That's what scientists believe regarding plate tectonics.